Let us talk CCA energy detect, or clear channel assessment energy detect. And what happens if I create a small signal, let's say 1 kilohertz wide, and introduce it to Wi-Fi to see what happens? Well, this is energy detect. In theory, if the signal is strong enough, it will bring Wi-Fi to its knees. It will just completely stop when it hits that limit. But what is CCA? I think it helps by explaining what we see in the standard, and then before we start doing all the cool lab stuff, with a couple of enterprise access points from Cisco and Aruba to see what happens when we introduce Wi-Fi to some non-Wi-Fi signals. Let us first then jump right into it and read a little bit from the standard. So here we have the standard, and you don't have to read everything of here, of course. This is from the 2020 standard. Here we have the CCA requirements, of course. So before we talk about energy detect, we need to talk about signal detect. That is the minimum modulation encoding range sensitivity. This is for a Wi-Fi preamble. So we can read this out loud here. So for the start of an OFDM transmission at receive level greater than or equal to the minimum modulation encoding range sensitivity minus 82 dBm shall cause the CCA to detect the channel busy, right? That means for any Wi-Fi, the minimum requirement is minus 82 dBm for any Wi-Fi preamble. That doesn't mean that like radios and clients and access point can demodulate in a preamble much lower than this. Of course they can. We have access point that can demodulate just a few dB above the noise level. I will come back to noise level soon. So this is just the minimum requirement, minus 82 dBm. And then we have the next one. So for this is for non-Wi-Fi. So additionally, the CCA mechanism shall detect the medium busy condition within 4 microseconds for any signal. Remember this one, any signal, with a received energy that is 20 dB above the minimum modulation encoding range sensitivity. That will be minus 82 plus 20, and that equals to minus 62 dBm. Okay, so that is the next one. And you have a small little note here. Small note here. The requirement to detect the channel busy condition for any signal 20 dB above the minimum modulation encoding range sensitivity minus 82 plus 20 resulting in minus 62 is a mandatory energy detect requirement for all class 17 receivers. Okay, so it's mandatory to detect this. And is there many ways how vendors may implement CCA energy detect, because should it always be minus 62, or should it be based on the radio's capability to be able to demodulate a preamble, etc. So this is what we need to look a little bit further. So we can start by reading from David Coleman's blog about how we usually, or most people think the energy detect how it may be implemented, right? So here is that one. So like I said, radios are able to demodulate preambles much lower than minus 82 dBm. So therefore, it could be that the signal detect is statistically 4 dB SNR, right, to detect a preamble. So if you had a noise level of minus 98, the radios could be able to demodulate a preamble Wi-Fi signal, therefore at minus 94. And then the energy detect would be 20 dB above that again. And remember, the signal detect will be quite variable depending on noise level or the current receive sensitivity, like all kind of reflections, people going past and changing all the environment, etc. So decoding things very close to noise level would be a quite dynamic or variable, right? So should therefore the energy detect also be that. So that is what we're going to test. You can look at an example here. There. So, for example, I'm going to read this out loud. If the noise floor of channel 36 was minus 95 dBm, the signal detect threshold for detecting .11 transmission would be around minus 91 dBm. And the energy detect threshold for detecting other RF transmission, like any signal that we read in the standard, would be 71 dBm. Okay, so then if the noise floor of channel 40 were minus 100 dBm, the signal detect threshold for detecting .11 transmissions would be around minus 96 dBm, and the energy detect for detecting other RF transmissions would be minus 76 dBm. So this covers the plus 20 dB, right? But this is always when I talk to Wi-Fi people, this is always what I heard is always based on 4 dBs and R plus 20 for energy detect, always. So that would mean, with that logic, of course, that would mean if I generated a signal that was exactly being measured at minus 96 dBm, perfectly minus 96 dBm, and the noise floor is minus 100. That would mean Wi-Fi would stop, right? Because it's energy detect. Then I could just artificially raise the noise floor to minus 91, use an RF generator to raise the noise floor to minus 91 dBm, because then it wouldn't react to the energy, because now it would be 71. So it would raise the noise floor because of the other transmission at minus 76, but it wouldn't stop Wi-Fi. So this could be how they do it, but if they did that, I could just raise the noise floor, artificially raise the noise floor if I had one other signal inside there to stop it. So this is what I want to test, but it can get a little bit complicated, etc. also for 20 and 40 mega channel, etc. So see how much time we have and how much time I want this video to be, of course. So let us move to how I'm going to test it and talk a little bit about some things like noise, etc. That is, I feel it's important. Yeah, so here we have the things that I want to test. CCA, a few possible variants. First one, a fixed value at minus 62 dBm. I don't think so, because then if you had a signal at minus 61.9 and it wouldn't stop, then it would have been a little bit difficult to have a fixed value at minus 62 dBm. So I don't think so. Next one, always 20 dB above the radio's capability to be able to demodulate a .11 preamble where noise is a factor. That would mean it always depends on the noise floor energy detect, because it's always moving 20 dB above the radio's capability, the radio's current capability to be able to demodulate a preamble at the lowest value. That is one way. That is usually the things that I hear the most. 3, so it's 20 dB above the radio's official lowest RTSA to be able to demodulate a .11 preamble, where noise is not a factor. Meaning that, for example, you tested your radio in a RF chamber, for example, before some FCC or any other compliant test, and you found out that your radio are able to demodulate at minus 97 dBm. So we set energy to minus 77, and that is a fixed value. It's always minus 77 no matter the noise floor, right? We should stop then, because that will be 20 dB above, right? Or we just play it safe and say it's 10 dB lower than ED, minus 72 dBm, because therefore we will not make any unnecessary we will still be compliant, because we will not, we don't want to have a value that is so close to the value, because or else we will not be compliant, right? So we just set it to minus 72 dBm and done. So this is the things that I really want to test, right? So what I'm going to do, right, I use an enterprise access point from Aruba, an AP735, a Wi-Fi 7 access point. And I have an antenna here that is going to create the sine wave, or an AM modulated signal that is approximately 1.5 kilohertz wide. Reason for having the antenna inside an RF chamber is because I'm sitting on the opposite side of this test, because I don't have so much space here to do these tests. And then I don't want my body to do too many changes of the signal that I'm creating. So that's why I'm using this RF chamber to block most of the signals that are going back, right? And I have this antenna is used for measuring. I recommend never to have antennas this close to another radio, so I'm setting the strength of this access point pretty low. And then I have another antenna here from another spectrum analyzer. I'm using the Aaronia V6 Econ V6 Plus. I forgot to mention that. But I'm using another antenna to create some noise. So I usually place this other antenna here on the back here, because this will be helped to test the number 2, where I'm artificially raising the noise floor to see if the signal that I'm creating will still stop Wi-Fi. So that is done. And to find out what the noise level is, I created this Grafana dashboard using SNMP, and here I'm able to pull the noise level for all current radios from the Aruba access point. So usually when I do this test, I have to wait a minute or so to have the correct value. I have some utilization from 2.4, 5, and 6 gigahertz, traffic, frames, etc., and the channel that it's using right here. So this will be helpful to see what the current noise floor is. Next one is the Cisco CW9178, also Wi-Fi 7 access point. I'm using the same test here. Antenna placement is a little bit different. The antenna placement for the test should be exactly the same, but remember there's different radios, different radio pattern. It's a couple of dB here, a couple of dB there. This is not an anechoic chamber test. This is just a fun test to show you energy detect, of course. But the antenna should be placed exactly the same for both tests. There. And then I built the Grafana dashboard for this one as well. It's a little bit different. Here I'm getting the noise level for all channels. I'm using the cleaner chipset. I'm able to get the noise level for all channels approximately every 60 seconds. So it'll take some time before I see the new noise level. I can, with the Cisco access point, I can join my client, and then the access point will report the current noise floor that it hears. So maybe we can see some differences there if I have time. So that's that. And little side note that I promised, a little bit about noise floor. It depends, of course. It depends on thermal noise. That is random electrical noise caused by thermal motion of electrons in any conductor. So it exists in all conductor materials, not just electronics. So in sensitive equipment like spectrum analyzers, it can mask weak signals. So there's always some noise, no matter what, and it really depends on how sensitive the device is. It also depends, of course, on the resolution bandwidth that you are using. Temperature and Boltzmann's constant is the constant value that we are using. And by using this formula, we can calculate the thermal noise for a 20, 40, and 80 MHz channel. Let me see here. So for a 20 MHz channel, we will have around minus 101 dBm. But of course, I never had minus 101 dBm because, of course, the clients add some noise on top of that. So usually 3 dB. So usually if you have a radio on a channel that is not being used by anyone else, it will usually have around minus 98, minus 99 dBm noise floor. And then you see for a 40 megahertz it's 90 minus 98 plus the 3 dB from the client, minus 80, 95, and 160 megahertz minus 92 plus the 3 dB, so approximately minus 89 dBm for 160, and then minus 89 on 320 megahertz, and plus the noise factor will be around minus 86 dBm for a 320 megahertz. There you see, like, if you had a 320 megahertz, then energy detect would be minus 89, minus 86 plus 4 for single detect, and then you're getting exactly at the energy detect marker, and that's why I don't think it's based so much on noise. You can see here a test that I did with my iPhone, where I can pull the noise level from the client itself. I can see the noise here, so from minus 98 dBm for a 20 megahertz channel, minus 95 for 40 megahertz, minus 92 for the 80 megahertz, and minus 89 dBm for a 160 megahertz. For my test, I will just use a 20 megahertz channel, so I will have around minus 98, 97, 96, depends on what other kinds of Wi-Fi channels I have around here, but I'm trying to use channels that are not used by anyone else, of course. And to end this little thing off, noise factor is therefore thermal noise plus noise factor plus anything that the radio cannot demodulate. So now let us see this test in action, or energy detect in action, by going to Aaronia and explain what we are going to do. So here we have Aaronia, the mission that I created. I removed myself video down to the right for this one, so we have room for all the cool stuff. Okay. So this is the mission that I created, is Spectrum 3D, the signal generator from the 2 antennas, and the waterfall. I can see how this mission looks like. It's not that difficult. I used the real-time mission for the V6 Plus. So we're looking at real time, so we'll use IQ to FFT or spectra block here to convert the IQ to spectrum, and then we visualize the spectrum in Spectrum Waterfall 3D. I use a calibration block for the antenna, Omnilog Pro antenna that I'm using for monitoring. I'm using an additional signal generator for Plus to artificially raise the noise floor if you're going to do that test. And the eco signal generator to create a narrow signal, and the eco. So it's not that difficult. So we can show how, for example, how the signal looks. We can add an oscilloscope here, just to add this one, and press eco there. So let's see, close this, and you can probably see how. Let's zoom in a bit. Yeah, so it's a really basic signal. It's an AM modulated signal, so this was not that exciting. So we're gonna delete this one now, and then we're gonna start the V6 Plus, V6 Eco. Yeah, so it's a really basic signal, AM modulated signal. So hopefully when we start this now, we will see the Aruba AP735 sending beacons, and this 3D view here. So I have this activated. I've shifted this a little bit to the left. So if I take this signal here and I generate it, you'll see we have this signal there. And for energy detect, we know what will happen, right? If I shift this signal inside here, we will stop it. I can just do that now and see, for no surprise, we stop Wi-Fi, right? Take it out, take it back in, out, back it in. It stops, right? So that's no surprise there. What I want to test is how low can I have the signal before it detects? And it will be, let's see there. It will be sometimes, I can delete the max hold here. Sometimes it detects it as something else, and then it stops. That is not the valid energy detector that I'm looking for. I'm looking for when it completely stops. So you can shift this in, and you see it stopped. Now it's really, really low, but sometimes when I do this and back again, it starts again. So now it was some false detection, I guess. So I'm going to raise it a little bit more, take it out, take it back in, and the same thing happens, right? It detected it as something else. So I'm going to take this one to -30, back in, happens again. So I'm gonna raise it a little bit more. There, now this one is at 29.3. Take it back out, back in. There. That's not 4 microseconds. So we set this to -29. There. Yeah, I think that's maybe good enough, right? So I set this here. So let it just stay here for a while. Just let it wait. And I'm measuring this at -79, of course, but that could be something else. So I'm waiting here, and let's see what the new noise floor is in Grafana. And of course, when I was looking for opening Grafana, this one started again. So this was at 29, so I need to raise it up a little bit. So this happens quite a lot, right? So let's say I added 0.5 dB again, so 0.4. Okay, 0.5 then. So it shouldn't be nothing. 4 microseconds is 4 microseconds, right? This bugs me a lot. Let's see. Let's say the 28. This is why all this test takes so long, right? And come on. 27. Okay, no beacons, hopefully. Okay, well, this jumps like it do this all the time, so I'm just gonna check the new noise floor first. So the new noise floor is at -73 dBm. The old noise floor was at -98. That was perfect. Now it's at -73, and the utilization is 99% utilization. So I'm getting almost 100% channel utilization by sending a 1 kilohertz wide signal inside here. Let's move it a little bit there. So that is what it takes usually to stop Wi-Fi. So it's not at 100 yet, right? So because it's still sending some beacons, I'm gonna raise it to -26 on this one. Yeah. So you'll see here the first, when you can see here it was -99, we see the noise level was 73 dBm. So that it's pretty spot on with -98 plus 4. That is -94 plus 20, around 74. So that fits the mark, right? So approximately 74, 72 dBm, I'm guessing. So just a little side note here, little funny side note. If I center this one, I'm gonna remove the Chrome a little bit here. If I center this signal to the same, and I place it exactly in the middle, now it started again, right? So the cool thing, or not cool thing, depends, is that in OFDM, you have this DC subcarrier at the middle, meaning it doesn't do any detection in the middle. So if I take the signal and I raise it up way above the energy detect limit, way above, it doesn't do any detection at all, because we are in the DC subcarrier. So here it doesn't do anything, meaning that if you have a signal, you want to transmit something, just center your transmission and have the width of the frequency less than the DC subcarrier, and then you can do absolutely whatever you want Wi-Fi will not stop. So I'm wondering if this raises the noise floor at all. And can open Chrome here, and you'll see here that nope, we like 5 gigahertz utilization is at 0.2%. Noise level is still high. Noise level is at, so it still detects it. So noise level is at minus 66 dBm right now. Minus 66 dBm. 0% channelization because we're hitting here in the middle, so it doesn't do anything. So that's cool. So I can, how strong can I do this, right? It's like -5. Okay, how high can I go? Can I go past the limit for energy detection, right? So again, I can make this video as long, super long, but I don't think we should spend that much of time. But now we also see some channelization because the signal is starting to get a little bit wider to the side here, right? So that was just some interesting thing that I found. So we can lower this down. What I want to test next is that if it's based on noise floor. Well, so that is an easy test. We can take the plus one here again. Let's see. Let's do this. Raise this up to where Wi-Fi stop. Let's center this list out to the side. Remove the Chrome window a bit, and then place this in here. There it stops. I'm gonna remove the max hold again. So it stops, but I'm gonna have it where it always stops. That was around minus 20, 29, 28. There stops. There stops. There stops. Right. So can I go a little bit lower than 29? Because I want the exact hard limit for when. Okay, 30. Let's wait until it stops there. So 21.9.0 or something. So having that here. So now I'm pausing it. Now I'm using the other generator. For this one, I'm just going to generate some noise, right? I can do this and raise the noise floor quite a bit. So I'm raising noise floor. You don't see that the noise floor has been raised here as much, because the antenna to generate this noise is the antenna is placed a bit further away from the monitoring antenna, but the noise floor is raised quite a bit now. So I can see this in the Chrome window here. And now the new noise floor is around minus 87 dBm. Now, with the other variant of energy detecting any energy detect being 4 dB, 4 dB as an alpha signal detect, that is minus 87 plus 4 dB plus 20. Okay, now it's 83. Okay, so really high now. So 4 dB above this again, 4 dB above 83 would be around 79, and then energy detect should be like 59 then. And then it's above the 62 limit, so that doesn't make sense, right? So that doesn't work. But either way, energy detect now should be completely different. So if I turn on the echo again, it stops. And does it stop at the exact same value? If I go to minus 29 and I go down to minus 30, 31, 32, and I move it out, move it back in, there, move it back in. So it actually looks, no, it starts again, so I need to go, yeah. Actually, more or less looks like to be the same limit. If I take this one and pause this again, all this noise, it's the same, right? It's exactly the same. So it looks like no matter how high your noise floor is, the energy detect will be the same value, right? Now we see from this signal, if I pause this, it starts again, and this one is raised, and we see all this noise floor here getting up. That was it from the Aruba access point. Now we're going to see what happens with the Cisco access point. So I'm going to stop this here now. I'm going to reload the mission, and we're going to remove the Chrome window, and we are ready to test the Cisco CW9178. Then we're going to start the V6 Plus first to do all the monitoring, and to no surprise, there is nothing on Unit 3 because the Cisco access point doesn't support it, and my Aruba access point was a US model either way, so I have access to all the channels. But nevertheless, so I'm just moving it a little bit to the side. We can do that here, for example, and then we can do main. You can also do this from the menu above here, but just do this. Let's see there. So I think it was here. So I'm going to shift it a little bit up. There it is. And I'm going to use a half as span. So we remove the DC spike and then shift it a little bit to the side here. There. And then we have this one. So I'm seeing that I'm using a little bit more signal like transmit power, I meant, on this access point. So I'm going to, yeah, probably going to lower that a bit. You can set it on the lowest since I'm measuring that close to the antenna. There. And remove the max hold. There is good. So it looks a little bit different than the Aruba one, right? And then we enabling the echo. This is 660, so I'm taking it into 6.5 to remove a little bit to the left. Take the echo 645. I can take it, and then echo signal generator, and then shift it to the right, and then that is all the way there, and then I can shift it there, right? So I'm gonna move it to a little bit higher, so 63, and remove the max hold again, and the same thing here. First I'm just gonna create the signal really strong and just enter it to the channel, and it stops right away, right? All the time. So that was not my goal. I want to find the signal where it stops, right? So then we are going to look at the Grafana dashboard. So to get the current noise floor, let's see if I can open that. So here we have, well, all the channels. So I only want to look at, I'm using channel 132 there, and this one measured it at minus 96 dBm. So a little bit more here, and they are on unit 3, so it doesn't support it. So I'm having it here, but utilization is at 2%, so it's basically nothing here. But this takes almost 60 seconds to load, so I will remove this Chrome here in the meantime. So I'm letting that just run, and then we're gonna find the lowest trigger for when it stops. So I'm gonna make it, let's see if I can, maybe I just remove max hold in the meantime. So I can just take the signal low, and I'm entering it in the channel. And now I'm gonna raise the signal until it gets detected. Okay. So you see here, it presumably didn't do any of the false detection or any other kind of detection that the Aruba access point did. Presumably, like if I raised it really low, it doesn't do anything that it stops. It just stops at the marker almost every single time. See if I do this, for example, 27.1, and I do this, start, stop, start. So now we're raising it 0.1 dB. Up, I'm just moving the mouse up and down. Minus 21, there, start, there, start, there, start. So I can do this dance. down, up, down, up, down, down, up, up. So that's, yeah. So the trigger value here is minus 27.0. Presumably there. Move my body a little bit. Same here, if I place it in exactly in the middle, this turns it, I can usually raise it up as high as I want. We're gonna have it on 20, what is it, 27.9. Let's see, no, I need to have it where I can stop it and start it all the time. So it also depends on where I have it, right? Because you'll see the radio pattern from different antennas, how they hear the signal, right? So here, there it always marks, and there you probably need a couple more dB, right? So here suddenly it's much higher than it is other places on the channel. And we can also see that almost when you see how the radio pattern is. It is a little bit down here, right? And it perfectly resembles that because it usually stops quicker, quicker there than it does there, right? So I'm gonna keep it where I need the signal the highest, all the way to the side here. And now I'm measuring it at minus 79 dBm. Chrome takes a little while to update, like usually almost every 60 seconds before it updates. So we will just wait for that one. And I see this is turning a little bit, so I'm just moving it there. So start, yeah, there. Now we're gonna wait for the reported noise floor. And hopefully I get that soon. Well, this bugger, stop. There, okay. So doing that, let's see if I can get the noise floor to be updated. It takes approximately every 60 seconds or something. But what we're gonna do in the meantime, I can just show you the Chrome window and see what happens there, right? So I raised the utilization up to 70%. Not 100% here, probably because it's still sending some beacons. I need to have it exactly at the stop marker. So there. Damn it. Seems like both type of access would do some sudden detections and it starts again. What we can do here, we can look in the 98 to 100 and we can go to cleaner statistics. No, to monitoring. Go to 5 GHz band. And usually, when it's high enough, we should get some sort of detection here. Oh, that was too strong. Usually, let's see if the Cisco had some sort of detection. Let's see. There. Continuous transmitter. Channel 132, duty cycle 100%. RCC, minus 73. Exact same value as Aruba access point reported it at. So usually the noise level when this, maybe it's a bug here. Okay, this is a little bit slow now because that was the last reported value. So now it's raised to minus 82 dBm. Channel utilization is at 100% soon. And this one reports it at minus 73. So I'm guessing, again, this value takes like almost a minute before it updates. Hopefully I find another Yang model that I can pull to get this a little bit quicker. But nevertheless, this is how it looks like now. And get it like almost 100% channel utilization by sending this small little signal in here. And the cool thing also with the cleaner chipset, if I place it in the middle, like 660, so 66 there. So you didn't see that. I can remove the Chrome window. No, I don't need to remove that one now. So I take this on the 0. And here I can create the signal like usually really strong. Let's see. Because this is in a DC spike again, so now it doesn't do anything. So I can make the signal super strong. And sometimes, maybe we don't get it in this video, sometimes we end up with clean air actually reporting on the signal at a value that is higher than the energy detect threshold. But we already proved that on the Aruba access point, right? That it doesn't do any detection inside the DC subcarrier, like right in the middle. So we see that almost out here, right? There's nothing there. So usually this one suddenly updates. Maybe we don't have time to see it here, but usually it updates with like minus 59, etc. Because this is higher, because I'm measuring at minus 63, so I'm guessing this is higher. So I can even raise the transmitter gain on the echo. Okay, that was a little bit too much. And maybe we see it. No, but approximately 74 here as well. So what I want to do here also, like raise this noise a little bit down, place it to there, and just have it here, right? So we're not doing anything now. Okay, let's do this. Maybe let's see when it stops, exactly when it stops. Okay, there, we know it stops there, right? So pausing this one, removing Chrome a little bit now, and we are enabling the V6 Plus generator. And if I raise this one up, you'll see that I'm raising this level a little bit up. There. So now I raised the noise floor. Now, and even though we can't see it yet on the Chrome value, let's see if we can show the Chrome now. Here regarding the how slow it was to update right now, it's been updated to the correct value, so it's minus 75. So around, I'm guessing around minus 70, around 74, 73, 72 for both Aruba and Cisco. It detects that, like, that's where it detects energy detect. But now I generate some additional noise, and then if I enable this one again, the energy detect value should be different, right? It shouldn't be detected at minus 74 anymore. It should be detected at a higher value, because now I'm adding additional noise from the other spectrometer. So let's play here now. It stops at the exact same value. Now, if I take the echo and I go down, so you see now, usually what I see, no, it looks, and now this stops, and I stop this other one. Now, there. So what you didn't see here, now I can remove the Chrome window again, right? The difference here is that energy detect, in this case, seems to work at the more noise, the energy detect is detected quicker. If you understand here. So here, instead of the energy detect being always 3 dB plus 20 dB, so before it was around 74 dBm, right? Now, because I added additional noise, now energy detect is detected quicker. So instead of moving above being detected faster, it actually detects now at a much lower value, right? So that is what usually what I've seen with the Cisco access point as well. Not always, of course, because it's many moving parts here. and then do lit play here. But again, it doesn't seem to be work like 3 dB plus 20 all the time. It seems actually to be more or less fixed value, almost around -74, 72. And if you add additional noise, it looks like at least the Cisco that use Qualcomm, I'm not sure, but it looks like if you add more noise, the noise floor is higher, the next strong signal energy detect would be detected faster, like lower than 74. It looks like that. I can't be completely correct here. But what I'm going to do with this access point for a last test before I end this video is to I'm going to enable a 40 megahertz channel, and then I do an associate to the network. So I'm let this roll here, and then this needs to be shifted a little bit there, so 5670, so that we have room for both of these. And this can also be shifted to 6170. I'm going to pause this one, and you're going to set it on channel 136 first. Then I'm going to enable a 40 mega channel. Okay, so now we wait. Maybe it detected something with all. I'd see this quite a few times when I do some of these tests. That, for example, Aruba access point detects as a radar and shift channels, and Cisco also could be some similar things because now it doesn't do any channel changes. So with the power of editing, hold on. Okay, there we have it. It took a while. This is what happens. Same thing with Aruba. When I do all this kind of tests, it detects it as an interferer, and they just refuse to use some of the channels for a certain amount of time. But I don't think anyone do this kind of weird test usually. So here now I'm using a 40 mega channel, and you can see this because I have an antenna placed really close, and then we get this intermodulation signal here that is being sent exact the same time as the beacon. This line here always disappear when you turn down 40 megahertz. This is only when you have it like super close, like I have my antenna. So now it's 40. So if I join this network, see, and then I take on that one, if I can associate, and this looks fine, right? I can take a speed test, and that is all fine and dandy, right? So what happens now when I do energy detect? So it's using a 40 mega channel with the primary on channel 132. I'm enabling the echo. That was a bit harsh. So I'm moving it to the right, and I'm doing this. You see that? Now, Wi-Fi didn't stop, but get this cool looking at there. Now it's a 20 mega channel, and now it's a 40. So this is the cool thing, we do the secondary channel. Wi-Fi still works, but it works better as I'm doing speed test and doing the signal up and down, and you see how it breaks the secondary channel. Usually if I make this signal strong enough, usually, okay, I got like harmonics there, so that was why I stopped there. Usually it's disassociates, right? So now I can move this signal there, and now you stop Wi-Fi, and now it works again. And now I do, okay, my phone, of course, a little bit smart and joined 6 gigahertz or 2.4 or something. So that is an easy fix, right? But there you have it. What happens when you use some energy detect on a secondary channel. So if you have some leaky PCBs, PCB electronics, etc., be careful on how you mount your access point. And now RRM kicked in and changed the channel. So I think we can end the video there. At least we were able to capture a cool little demo of what happens when you pull the signal on a secondary channel as well. Wi-Fi still works. It'll just use the 20 megahertz channel instead. So let us just end this video now. And yeah, that's it. So I hope you learned something, or we were able to visualize something. So this is a cool test, and I've been spending a lot of time doing all these tests, and I haven't been able to do everything in one video. This is just something that I just promised to share. What happens when you send a signal and trigger energy detect. And it was cool that my hypothesis was correct, that if I have the most narrow signal that I can create, it will still trigger energy detect. And this is one really important reason on why you should have a minimum of 1 to 2 meters of distance of any other electronics when you install your access points, because you could have something else leaking a signal that would trigger energy detect, and it will just stop Wi-Fi and bring it to its knees. So I hope it's been an okay video, and see you in the next one.